Okay, no, nice. So for the next talk, we have three speakers: Chris Birkbeck, Sidharth Hariharan, and Seewoo will talk about the eight-dimensional sphere packing in Lean.
Thank you very much for having us, Patrick, and thank you for the introduction. As many of you know, there's an ongoing effort to formalize the 2022 Fields Medal winning solution to the sphere packing problem in Dimension 8, being led by myself, Chris, and Seewoo. I'm going to briefly uh, give an overview of the sphere packing project, the different areas. I'll talk a little bit about the so-called magic function that Viazovska famously constructed, and then Chris will give an overview of progress on modular forms. Seewoo will give an overview of derivatives, quasi-modular form inequalities to wrap up the proof that the magic function actually works. And then we have some concluding remarks and acknowledgements. So yes, an overview of the project, where we're at. So I'm sure you're all aware of what the sphere packing problem is, but nonetheless, it asks the question of how we can most densely pack Rn with non-overlapping n spheres of the same radius. And Viazovska showed in 2017 that the densest arrangement in R8 corresponds to spheres where the centers lie on points on the E8 root lattice. So the E8 lattice looks, well, I shouldn't say it looks like this. I don't know what it looks like. I can't see in 8 dimensions, unfortunately. How much fun would that be? But here we have a projection of the root system on onto a certain plane, and what so the way that this lattice looks is it looks like this. Sort of, it looks like the z span of whatever's projected onto this plane. And in this picture, nodes correspond to vectors and edges correspond to nearest neighbors. So as you can see, the connectivity of this graph should suggest that indeed the E8 lattice is quite dense in R8, and this is the intuition. And it was long suspected that E8 is the optimal sphere packing in R8. And in 2003, there was a method proposed by Cohn and Elkies that they essentially in Cohn's 2022 ICM paper, he writes that he thought that they had solved the sphere packing problem when they came up with this method. And indeed, this method turns out to be key, but it turns out that there's a hugely non-trivial step between these linear programming bounds and actually solving the problem. So what they showed was that if you can have, they showed essentially that in for any dimension n, you have a family of upper bounds on all sphere packings in Rn, indexed by functions that satisfy certain very special properties. Unfortunately, constructing such functions is rather difficult, and it's even more difficult to find a function such that the corresponding upper bound in R8 is precisely the density of the E8 packing. And this is what Viazovska did using the theory of modular forms. So let me talk a little bit about how the sphere packing project got off the ground. So it all began in 2024 when I was an exchange student from Imperial College London at EPFL, which is where Maryna is based. And we embarked on this collaboration. It was announced that we were going to work on this at a workshop in June of 2024, but we worked closed source for about a year before going public at Big Proof. So here we have a very nice animation created by David Renshaw of the Institute for Computer-Aided Reasoning and Mathematics that shows the evolution of the blueprint over time. So this is completely, it was disconnected at the beginning. Then we started connecting the nodes together. This was 2024. And then in maybe September 2024, October 2024, I started working on part of this for my master's thesis with Bhavik Mehta at Imperial College London. And you can see all of a sudden the number of contributors, the number of contributors is increasing. You can see that below. And this is after going public at Big Proof. As you can see, the project has evolved quite a bit, but the blueprint, this is accurate as of the 18th. And I don't think we've actually made too many changes to the blueprint since the 18th, which was 3 days ago. So there's a fair amount of green, but there's also a fair amount of white. So there's a lot of work that still needs to be done And this is very much an active project, and we will outline in this talk ways for people to get involved. Um, so yes, so project areas. Well, there's basic sphere packing theory. This is an area of the project where we've defined a sphere packing. We've defined what it means for a sphere packing to be periodic with respect to a lattice. And we've proved some basic API to use these definitions, basic lemmas about these, like density formulae. We've also proved some basic facts about the E8 packing, and recently Bhavik Mehta showed what the density of the E8 packing is. Um, the second thing is this method proposed by Kohn and Elkies, where you have this family of bounds indexed by these special functions. And this over here, there's been quite a lot of work, but so we have an outline of the proof, but unfortunately, there are still some remaining goals involving summability, as well as there are some refactors that are necessary as well. But maybe the biggest to do from this area of the project is the Poisson summation formula in RM. And there is some work being done by Aaron Lin and Bhavik Mehta, but it's at a fairly rudimentary stage, and we need to. This is an active project goal. Uh, Modular forms theory is another area, and this is something that Chris will talk about in more detail. Um, Constructing the magic function is something that I'm, again, very actively working on. So constructing the special function from R8 to R and proving that it satisfies certain properties, such as being a Schwarz function. We need to show that two sub well, the function itself is constructed. I'll talk a little bit about how it's constructed in some of the remaining goals. There's some to-dos, but there's been a lot of progress lately on this area of the project. And finally, there's proving the modular form inequalities, which is Seewoo's area of expertise. So the first, second, and fourth areas of the project are being maintained by myself. So I usually review PRs that come in for these areas. Chris maintains the third area and Seewoo the fifth. So a little bit about the magic function. So if we have to define the magic function, it's a radial Schwarz function. So it only depends on the norm of a vector, and it's smooth and it's rapidly decaying. And it's defined as a linear combination of a function A whose Fourier transform is itself and a function B whose Fourier transform is its negative. These functions are defined as follows. I'm not expecting you to remember these gigantic integrals, but one diagram that's useful to keep in mind is this one. So what happens is each function is defined as a sum of four integrals in the original paper. We've broken these contours up into, so this contour is expressed as one contour plus another contour in our repository, this one as this contour plus that contour, this one is that contour, and this one is that contour. So we've actually got 6 integrals in our repository for A and 6 integrals for B, and then G is a linear combination of these guys. And if we want to define the magic function in A, I'm just going to show how we've defined, defining it in lean. I'm only going to show how we defined the +1 eigenfunction A. So we first define the integrands as these functions in terms of some function phi naught, which is defined in terms of the Eisenstein series of weight 2, 4, and 6. And then we define a real version of this, which is this composed with a parametrization. So this corresponds to the parametrization of the first contour, phi2 to the parametrization of the second, and so on. And then we define 6 integrals I1 primed up to I6 primed, which go from R to C. And then we have an I1 up to I6, which is these guys composed with the norm squared. And then we define A primed from R to C to be some of these guys, and A to be that composed with the norm squared. And active and remaining goals for this part of the project. So proving that I1 primed up to I6 prime are Schwarz functions in R. These guys are Schwarz in this input here. This is done minus modulus and smoothness results. Then moving from 1-dimensional to 8-dimensional Schwarzness is actively being worked on. Proving that these are integrable over appropriate intervals is also something that's actively being worked on. Proving that A has double zeros at lattice points, proving that it can be expressed in a certain alternate form is a very important project to do, and this was mostly completed at Italy in 2025, but there are some to-dos remaining, and then bounding some integrals. This is something that I will do in a bit. And there are many more goals. So if you want to get involved and if you want to know more about these goals, we have these weekly meetings called packathons, which take place on Tuesdays at 10:30 a.m. Eastern Time. We will have one next week, and there's a Zulip thread where there's more information about this. So Chris will now talk a little bit about spaces of modular forms.
Great, thanks. Hopefully I can share my screen once you stop sharing yours. I think, yeah, okay. And hopefully you're seeing my slides.
Yes.
Great. I make them full screen again. All right. So yes, I'm in charge of the modular forms side of things, and I just want to tell you a little bit about the work that we've done and that's how it's arriving into MathLib. So, hidden inside of Sid's magic function, there was a bunch of things called modular forms. And if you don't know what they are, these are just special holomorphic functions which have nice symmetry, so transformation properties in terms of some action of the matrices, the determinant one, the SL2Z, on the complex upper half plane. And the definition is there in the first bullet point if you're kind of interested. And these show up in number theory, and we care about them for lots of different reasons. And they tend to be the keys to proving this sphere packing. And when Sid started working on this project, well, when he contacted me, I had been working on defining lots of examples of these modular forms, especially things called Eisenstein series. And these are exactly the sort of things that we need to construct our magic function. But one of the things we needed is we need to prove a lot of identities between them. And a lot of the arguments that you rely on are you have some horrible combination of modular forms equaling some other horrible combination of modular forms. And the way you prove this is by saying, well, these are two things that live in a one-dimensional space, so they have to be the same up to some constant. And being able to say, oh, this space is one-dimensional, having exact formulas for the dimensions, that was the big one of the big modular forms inputs that we had developed for this. And we did not want to know just that they were finite dimensional, but exactly what their dimensions were. And there is work in progress by David Loeffler to do this and generalize this just to prove finite dimensionality in general for other levels, but that's not quite done yet. But I want to just describe how we did this and how it differs from how you'd normally do it in a textbook. This is the theorem that you want to prove is that the dimensional space of modular forms is, the modular form is defined on a parameter called the weight, which is this k, and it's either the floor of k over 12 or that plus 1, for example. And this is the result that we've proven, and it's sorry free in our repository. So this is done, although it's not been PR to MathLib yet, and it's ongoing. But that's a not very cleaned up version of what that theorem says. And as I mentioned, normally you prove this. It's not so bad. You prove this because you have complex analysis, and it boils down to doing some tricky contour integral, which can be done by hand, but we can't do it in Lean. It can be done in Isabelle, for example, but we haven't really developed enough contour integral stuff to do this. So that goes out the window. So the strategy here was a different one. We used the maximum modulus principle to prove by hand that spaces of weight zero modular forms are just one dimensional, and negative modular forms they're empty. And then we combine this with using a special, not quite modular form, which is called E2, which is like the main source of pain for this whole approach. And it's this double sum that I have written down here, and the reason that it's double sum will come apparent in a second. This special not modular form allows us to construct an actual modular form called delta, which is gives you like the Ramanujan tau coefficients and so on. And we also need this for the other bits of the project for defining like Serre derivatives and so on. And this not modular form is just you define this special non-vanishing modular form. And the key is once you have this non-vanishing modular form, you can sort of using the two dimensions that you have, you can just start multiplying by this and you move up in 12. So you can divide by it and you move down by 12. And that gives you enough to prove it. And the problem with this not quite modular form is that it's not quite a modular form because the action of the upper half plane, here, I'm not sure if you can see my mouse, but if it was a modular form, it would, on the first line, it would say E2 slash gamma is just E2. But there is this horrible correction factor that shows up. And that's what breaks. But it turns out that if you take its logarithmic derivative, so just f primed over f, then it's of the 24th root of the delta function that we have, then it is exactly this E2 function. And this lets you prove that your delta, as I defined here, is actually a modular form, which is kind of hard to do just from this definition because it's just a Q expansion. But once you have this, then you're golden. And so it all boils down to just proving how this not quite modular form thing behaves. And it all comes down to, said that this sum wasn't quite absolutely convergent. It matters in which way you order the m and the n. You do the sum here. And the theorem the main tricky thing is, you have this theorem, let's ignore this symmetric ICO for a second. It just says if I sum over n and m of, mz plus n minus mz plus n plus 1, then you get 2 pi I over z. And if you swap the n and n, you just get 0. And this is something that happens obviously because it's not absolutely convergent. But before doing this, we didn't really have an API for doing non-absolutely convergent sums or conditionally convergent sums. You could do some hacks, but nothing quite polished. And so we had to develop this. And so together with David, we made some API for this. And I sort of want to highlight one neat thing, that the original definition that we had for uniformly absolutely convergent sums is the first definition here. This is the multiplicative version, where you say, well, it's just some limit which over some filter, and the filter is this at top filter, which is like as you go to infinity. And you say, well, no matter what finite sets you go through, as you go to infinity, you get some limit. And we wanted to change what this filter was to some more general filters. And when I started doing this refactor, it was kind of painful because we use this a lot. But one thing that David noticed is that we could use these optional parameters, which is this thing here, this L, which says, well, if I give it the parameter, then use it. But if not, then just default to the one that we had before, which is this at top. And this really made the refactoring much easier, and it saved us a whole lot of time. So this is now been implemented in MathLib. This is one of the things that came out of this sphere packing project. And using this, we've now defined like E2 in MathLib, and there's PRs in progress defining all of this. And soon we'll get up to the, well, soon. Hopefully we'll soon have the dimension formulas for level 1 and infinite dimensionalities done. But yeah, I just wanted to highlight one of the things that we've been using this for. And then now I think Seewoo will tell you about how, well, improving some identities which also use E2. No, let him go.
Yeah, thank you, Sid and Chris. Let me try to share my screen. So can all see my screen right now?
Yes.
Thank you. So I'll wrap up the last part about the derivatives of quasi-modular forms and the modular form inequalities. So there are some properties that magic function really needs to be magic, where it should satisfy some linear constraint, like the function is non-positive and its Fourier transform is non-negative. And then those two are written in terms of the quasi-modular forms, and they eventually reduce to those two inequalities where f and g are certain quasi-modular forms. Like in terms of Eisenstein series, or h to h4 here are the powers of Jacobi zeta functions. And there are essentially three informal proofs of the same inequality, where there is an original proof by Maryna using certain theorem on the bounds of the Fourier coefficient and use interval arithmetic. And there's a second proof by Dan Romick, which uses new modular form identities and some explicit values of those modular forms at phi equals to I. And the last one is by myself, which uses modular form identities and some theory about the positivity and the derivatives. And we decided to formalize the last one because that was the easiest to formalize. So here are some informal, like very brief sketch of the proof. So first of all, the first inequality is easy because f and g are both positive. So we'll only care about the second one. And the idea is simply that f over g itself is a monotone function in T. And then you can compute the limit as t goes to 0. And then the limit is exactly the constant show of the inequality. So that's what we're going to prove. And the limit can be computed using the transformation laws of f and g, which can be derived from E2, E4, E6, and that of set of functions. And this monotonicity simply follows from a lot of identities between quasi-modular forms and their third derivatives. And those all can be proved using Ramanujan's identities about derivatives of Eisenstein series. So let me tell you more about those identities. So basically, we have a definition of D and third derivative as follows. So D is here a normalized derivative of a modular form, normalized by the constant 2 pi I because it makes everything prettier. And third derivative is a derivative with the correction term, which is a multiple of E2. And then we already have some basic theorems like how they act with respect to addition, subtraction, multiplication, constant multiplication, and how it acts on the Q expansion where you simply get NAN for the nth coefficient from AN. And there are already formalized but not yet merged PRs by Cameron and Claude, where we really need the Ramanujan's identities about the derivative of Eisenstein series. And we also need similar identities for this set of functions. And last two uses the dimension formula for the level 1 mentioned below, previously by Chris. And we also made some APIs to consider these functions as a function only on the imaginary axis. So we simply just restrict this as a function on R. And then we also proved some basic theorems about this, like about addition, subtraction, multiplication, where like if you add two real things and you will again get a real stuff and so on. And we also have like the realness of the basic modular forms or quasi-modular forms, E2, E4, E6, and H2, H4, and positivity of some of them or their derivatives. And there are some auxiliary theorems where something like if derivative is positive and f itself is positive for large t, then itself should be positive. And there's also some lemma that is in progress where third derivative, if third derivative is positive, then f itself should be positive. There are certain conditions. And something interesting is that you can even like register those to font prop tactic. And that somehow makes things a little bit easier to work on, like proving some quasi-modular forms that are already a combination of like ET46 is real or positive. You don't need to write long proof for that. You can just simply use font prop to do if you register those as a font prop. So for example, we had some proof like this before, which says that like this f, which is E2E4 minus E6 square, is real, and you can unfold that and use those basic theorems to prove that it's real. But like if once you have registered all those basic theorems to font prop, then you can just prove it in a line, which basically do almost the same thing. And then another thing you can do is that you can do the same thing for n differentiable, essentially the homomorphicity of the modular forms. So we can add those, like those m differentiable as sub neg already exist in Mathlib. We just locally register to the font prop. And additionally, we add like E4, E6, and a set of functions m differentiability as a font prop. And now you can do the same thing where whenever you want to prove differentiability of something like E2 plus E4, E2 times E4, you don't need to write down all those things. You can just simply do repeat font prop. So that just like makes life easier. So that's what we have right now. And the remaining goals are we first need more modular form identities and positivity result. But those are essentially already done by the existing PRs thanks to Cameron and Claude. And we also need to prove the limit, and that will eventually finish the proof of the inequalities. And the most important part is to actually connect them to the magic function and see how this reduces to the modular form inequality. And the last thing is about like upstreaming some of those to the master lib, where we are planning to upstream the derivative and the third derivative and prove like this theorem where like the third derivative preserves the modulority to maslib. And we also have a proof of the Jacobi identity, which might be upstream to maslib later. So let me just wrap up the presentation. So first of all, if you are interested in this project, anyone can be involved to the project. It is public, as you saw before. And then you can scan the QR code to find the repository, or there is a Julep channel for our project. And don't forget to come to our weekly hackathon that happens every Tuesday at 10:30 and Eastern Time. And that will happen in Zoom, where you can meet us and discuss about some PRs open there. And also all those links can be found in the project website. So we thank to many people. First of all, we thank Maryna Viazovska on like initiating this project. And also thank to Kevin, Bobek, and many people at Pittsburgh, including Jeremy, David, and people at Hoskins Center and ICARM. And also Utensil Song and Pietro. And lastly, we thank all our contributors here, like probably 28 of them. And those include humans and non-humans, including Aristotle, Claude, and Gauss. I guess that's all for our church. And thank you for listening.
Thanks.